In this video, I'm going to demonstrate how to establish UART communication with a computer. Some of the things we'll talk about in this video is adding an external clock, and this will most likely be a crystal. Instead of polling to receive data and transmit data, we will use the interrupts. And we will make the microcontroller do something when we receive data from the computer. Let's first discuss the external clock. Why do we need an external clock? In the previous UART videos, we connected two AVR microcontrollers together. And we were using a baud rate that was slow enough that the internal clock source was able to establish a communication that had less than 1% or a small or an acceptable percent of an error rate. Communicating with a computer, you may not have the option depending on the application. So we need to find a crystal or a clock source that has a frequency that is acceptable to baud rates and that will be able to communicate with an error rate that's acceptable. These are what clock sources look like. These are crystals, the ones in the metal casing, and the ones you'll see that kind of look like capacitors. These are resonators, ceramic resonators. To make sure that these clock sources operate at the correct frequency and that they're stable, we'll also need to use capacitors. Capacitors are selected by manufacturer suggestions on the actual crystal or ceramic resonator and the residual capacitance that you have on your PCB or on your breadboard. I don't know what I have on my breadboard, and it's going to be changing from the breadboard to the PCB, so I'm not going to use any formulas or anything to select the resonator. I'm just going to use what is recommended in the data sheet and within the range. The closer you get to the actual range or the actual capacitance you need will give you a better and more stable circuit and more stable frequency. So it's best when after you design your PCB, you can measure that and also get the data sheet for the crystal and determine what resonance or what capacitance you need for the crystal. A good rule of thumb is just to use a 22 picofarad capacitor. These are 22 picofarad. The formula that you would use to determine the capacitors is load capacitance times the residual capacitance on the board. This one is specified by the manufacturer. This one would be the capacitance you have on the for the traces and whatever you have on the board. And all of this is multiplied by 2. But like I said, you're probably going to be fine with 22 picofarad. Additionally, the error rates for the baud rates that we're going to be selecting will be low enough that there will be some wiggle room in here. We're not going to be creating anything that would require a very precise clock, so what we're doing here with 22 picofarad is fine. On the ATmega 324, the crystal is connected to the XTAL pins, XTAL1 and XTAL2. The XTAL1 is on pin 13 and the XTAL2 is on pin 12 for the ATmega 324P. And the schematic symbol is a rectangle or a square with a couple lines next to it. And then the capacitors are connected back to ground. Let's take a look at the data sheet and see if we can find a suitable crystal with the frequency we can use for communicating with the computer or a baud rate that we select. So let's take a look at the data sheet. If you don't know how to get to the data sheet, just go to Google and type in the part number and data sheet, the word data sheet, and then you should have that in the first few results. Okay, what we need to find is the area that will specify what clock source frequency would be acceptable for UART communication. So we're going to go to the UART section of the data sheet, and the portion you're going to be interested in is way on the bottom, and you'll see 3 tables. Here you go. In the beginning, it starts out with 1 megahertz, and it gives you these values. We've actually looked at these before for the device-to-device communication, and we were using something very, very slow, like 2400 baud or 4800 baud, I can't remember exactly, but these were acceptable limits or acceptable error percentages. You'll notice that there are crystals that have 0% error. So like I said before, even if you have a little tiny bit of fluctuation in the frequency, in this particular application it probably won't hurt us. You'll notice that the 2 MHz has quite a bit of error depending on what speed, baud rate speed that you use. And this is the baud rate speed here. And it starts at 2400 and it ends at 250,000. And you'll notice that with the exception of this single percentage using the single speed asynchronous communication, it has a negative 25%. So we'll not even look at that. We're not even going to be interested in that one. You'll also notice that these frequencies look really strange. I mean, they're not a rounded number like the 2 MHz or 1 MHz. They have a specific number, and these are very popular clock sources because they're made for this type of communication. And at the bottom it also specifies what the maximum is. The kbps, or you'll see baud rate bps, this is bits per second, and this is 1000 bits per second, or kilobits per second. Let's take a look at some other choices that we have. We have 3.6864 MHz, which also has a pretty good error percentage, very low, except when it comes to the upper baud rates. Again, the 4 MHz, very high error rates, so we're going to not look at these. But you'll see another odd one. It's 7.3728, and it appears to have the same error rate at the sort of the same moment or the same area. Let's take a look at a few more. Another one is 11.0592. We can still see that negative 7.8%. And we have the same thing going on with the 14.7456. And then we have the maximum for this particular microcontroller, because this microcontroller has a maximum of 20 MHz. We have 18.4320 MHz. And you would select this if you're doing a lot with the microcontroller. If you have a lot of instructions in there outside of doing the communication with the UART, you want some reserve. It would be best to go with something at the higher end. But you still will notice that your maximum is still 230.4K. You can't go any higher than that. Let's take a look at the highest one we can do for the 1.8432. You can see the highest we can go with that is 115,200 bits per second, or 115,000 bits per second. And this is probably going to be faster than I need it. This is sufficient for what we'll be doing with communication to the computer, and we don't really need to use this high level baud rate. We can go with like 9600 or 14.4K. So let's take a look at how we need to change the fuse bits. And from the previous video, we know that we have to go to memory programming, and we'll go down to the low fuse byte. This information here, this is where we select our clock source and select our startup time. This information doesn't really tell us much. It gives us what the defaults are, but we need to know exactly how to configure the fuse bits according to what crystal we have. And over here it says see table 6.1 on page 30 for details. You can also see on 6, it's the system clock and clock options, and this is what we want to do. Go here. And you'll start to see a lot of information about how the microcontroller works with clocks. And you can see that the table 6.1 that the low fuse byte table gave us is giving us the options for the clock select, and from bits 3 to 0, 3, 2, 1, and 0. And they have several options: low power crystal oscillator, full swing crystal oscillator, low frequency crystal oscillator, internal 128 kHz RC oscillator, calibrated internal RC oscillator, external clock, and then reserved. We still really don't know what we need to use, so we need to find out more information about the low power crystal oscillator. So let's take a look and see if we can find the low power crystal oscillator section. You can see the connections are here, just in case you need to look at that. And here we find the low power crystal oscillator section, and you can see that there are frequency ranges: 0.4 to 0.9, 0.9 to 3, 3 to 8, and 8 to 16. And I actually changed my mind. I'm not going to be using the 1.84 megahertz crystal. I'm going to be using an 18.432. So we actually don't have a selection for us here. Because mine isn't listed on this table, I'm thinking that I really don't have a choice but to use the full swing crystal oscillator. After a tiny bit of research, I found that actually full swing mode is something you can set to provide more stability with your existing crystal. So I'll be using the full swing mode, and because I have an 18.43 megahertz range, it fits this megahertz range anyway, so frequency range. Now let's take a look at the startup time and the 0, because actually this is the setting for clock selection 3, 2, and 1. We now have the 0 to deal with, and then the startup times. So let's try to determine what startup time and clock selection 0 we need to select. You can see that we don't need any of these. These are ceramic resonators, and we don't use that. And here is the section for crystal oscillator. We have the BOD enabled, fast rising power, and slowly rising power. The BOD stands for brown out detection. We're not going to be using that, so we can eliminate that as a possibility. My limited research tells me that the startup time allows the crystal oscillator to get into a stable frequency. So I'm going to go ahead and select 65 milliseconds as the startup time, because this is the slowly rising power, and it's going to provide the most time for the crystal to establish a stable frequency. So now we know that the clock selection 0 bit needs to be 1, and the startup time 1 and 0 are both 1, which means unprogrammed. So after looking at the datasheet, let's see what we have to change for our settings. These are the default settings for the low fuse byte. The dividing by 8, I'm going to go ahead and unprogram that because we don't want that to happen. We'll keep the clock out as unprogrammed because we don't need to sense the clock. And the startup time, we are going to make those both unprogrammed. So this one is going to have to change. And clock select 3, 2, and 1 is 0. Mark that one out. 1 and 1. Now we need to change the low fuse number. It's actually all ones except for 1, 0. 1, 1, 1. 1, 0. 1, 1, 1. Let's put together a circuit. We won't be putting the crystal on in the beginning because I want to make sure the microcontroller is working, and we're going to program it with a blinking LED so we can look at the timing of the LED, the way it's blinking. We'll do it blinking 1 second. It'll be on 1 second, off 1 second. And then when we change the fuses, we'll rerun it and see how the LED blinks. It should be blinking a lot faster, like 18 times faster. So let's go ahead and put the circuit together. I'm going to be using the ATmega 644 because I can't find my 324P. This is the 644A. Fortunately, the 644A shares the same fuse bits as the 324P. I'm going to add an LED. And we'll connect it to the pin B0. If you don't know how to put the LED in or do the circuit, you can always refer back to one of the earlier videos where I have a very thorough discussion about, or demonstration about, the LED and the circuit. I'm putting the ground and VCC on this side because it sometimes gets in the way when I have it on this side, like I had in the previous videos. And finally, the programmer. Okay, we'll go ahead and write a program and let this LED blink or toggle every second. Okay, we'll use the Atmel Studio for this. And we'll create a new project. And we'll call it LED Crystal Test. And the device I'm using is the Atmega 644A, and that. Okay. Alright, it gives us our skeleton code. We're going to move this. And we're going to add a couple things. First we'll add a delay. The delay utility. And we're going to set up the port B data direction. Or actually just the pin B setup. And then we'll toggle every 1000 milliseconds. So B, toggle. And if you need more explanation on this, just go to the NewbieHack website and look up toggle or look up the LED blink, and you'll get a good explanation. B0. And we'll wait for 1000 milliseconds. So every 1000 milliseconds this should toggle the pin B0. There's another define that I need to create, and that is the FCPU. And this tells the compiler that will be this is going to be the actual megahertz, or the hertz. It'll be 1 million, and it's an unsigned long. Save it, and then let's see if it builds. I didn't put the B here. BDRB. Alright, let's try again. Looks like it built. And make sure we have the 644. We want to be in release. So that's what I created the tools. And we'll plug in the programmer, and let's see if it builds, or it programs. It doesn't seem to want to program, and it says LED crystal test and then the release. Let's go into that folder and see why it did that. Right. Huh. Yeah. Oh, I got debug. It's strange that it has a debug folder, but here I said release. It's very interesting. Let me see. Let's go ahead and do that again and type in. Oh. Let's try building it again. Maybe I built it incorrectly. Go back to that folder and see if it made it. Yeah, now I got a release. It's strange. I must have clicked on the wrong build, or this was in debug while I was building it. That's probably what happened. Okay, so let's go ahead and do this again. Now it should work. It worked. Okay, we can see that it is blinking. It's on for a second, off for a second, on for a second. So it looks like it's working correctly. So let's go ahead and burn the fuses and see if we can get this thing to go faster, because that's what. And with and installing the crystal, this should blink 18 times faster. I'm going to show you a cool trick that it's better than going to the command. Normally, or typically, we would go to the command prompt, or the DOS prompt, and we would type in AVR dude. Then we would type in all the parameters, -p, then the part number, -c, and the USB tiny, and then we would do the -u, and then we'd have the what we'd want to put into memory. But let's do this a different way, because I don't want to keep typing this over and over again. If I want to go back to default, then I'd have to retype everything, or if I made a mistake, I'd have to retype it. So better, I'm going to use what is called a batch file, and that just entails me going to Notepad and just typing it in here instead, but naming it as a batch file. So let's go ahead and put in the AVR dude and all the information that we went over to set the fuses. So it was -c, USB tiny, -p, and this one is the 644A. And then we have the -u, and this will be the high fuse. We're going to use the right and the binary number. 11011001 is the first one for the high fuse. M for immediate right. The -u for the low right. This is where we made most of the changes. So let's go over the actual number just to confirm we have the correct number in here. The high fuse we have for the ODC, that's the on-chip debug. We had that as unprogrammed, and we changed the JTAG to unprogrammed. We want to use port C, and the rest of them are default. The SPI is programmed, the watchdog is unprogrammed, the save the EEPROM is unprogrammed, boot size, this is default 00, and then the boot reset is unprogrammed. So let's go to the low fuse, and then this one is unprogramming the divide by 8 for the clock. Unprogram the clock out, we don't need a clock out on port B. We are unprogramming both the startup times, so we get the 65 milliseconds, And then the next 4 is the 0, 1, 1, 1, which is 3, 2, 1, and 0 for clock select. And the 0, 1, 1 was for the external full swing oscillator. And the last one was for it to be a crystal. Make sure we have the M's here and the colons in the right place. L fuse, H fuse, dash U, dash U, dash P. Okay, everything looks good. And then, so we can see what happened, we're gonna use the word pause. This is a command in the batch file, which allows you to click any key or press any key to continue. So we can see what it says after this executable and the parameters have executed. So let's go ahead and exit, and actually no, let's save as. This is really important. You don't want to save as a text document. You want to just use all files, and then we're going to name it set uses for external crystal full swing. Okay, and then we're gonna use the .bat. That is short for batch file. Batch. We could actually put many commands in here, and it'll run one at a time. So this is a lot easier and a lot more functional than going to the command prompt and typing all that stuff manually. And then if you got something wrong, then you have to go back and do all of it over again. So let's go ahead and save this. Make sure it's saved in the desktop. Yeah, good. Save. So let's get out of that. We have it right here. So all I have to do is double click it and hope for the best. Okay, it looks like I got something wrong here. Let's see what we have. It looks like I didn't put in the M644A in correctly. So let's see what the correct one is. Okay, I may have to just put 644. Let's try that. This is what's convenient for using a batch file. One thing that I don't like is when we exit and we save it, it thinks it's open still, so we may have to rename it. So let's just use 644, save it, see if it works. No, the process cannot access the file because it's being used by another process, so we'll save it as a different name. We'll use number 1. Save. Okay. Oh, we didn't do it with the batch file, so try it again. Save. Okay, that's all files 1.bat. And you can tell it's a batch file because it has these gears in the icon. So let's make sure this is the correct one. That's number 1. Try it again. Okay, it looks like it did something. So we have this device signature correct because it accepted and it actually did the process. So let's go over the actual process to explain what's going on here. Okay, the reading was complete. The device signature, it gives you the device signature. It gives you the input file, which is what we put in. It wrote what considers a file, the binary, and it writes it to the AVR. Then it's verifying it to make sure it is actually written correctly. Now it's going to read the chip. It's going to verify it, and then it states that it's verified. So now it does the same thing to the low fuses. Looks like it verified correctly. So we can go ahead and press any key and see if it worked. Okay, we're going to add the crystal and the capacitors to the pins 12 and 13. Obviously, we can't run it until those are plugged in because what we've done is we set the fuses so it cannot use the internal oscillator anymore. And now it has no clock signal to use as a way to function or as a way to actually carry out instructions. So we have to add these components to the microcontroller, and as it sits now, this microcontroller is just a brick. It will not work unless you have the crystal or some oscillating device that will work with the configuration that we've set. So let's go ahead and add the crystal to 12 and 13. Let's add the capacitors to ground from 12 and then from 13. And now we can plug it in and see if it works. We should have a fast blinking LED. And sure enough, it worked. You can see that the blinking is very rapid now. It's because we're using a crystal that has 18.4 megahertz rather than using the internal oscillator set at 1 megahertz. So what we need to do now, in order to make this blink at 1 second intervals again, we need to change the FCPU define statement to the correct setting for this speed, the 18.4 megahertz. So let's go ahead and do that. Okay, let's get back to the program and put in the correct 18 megahertz. Let me see what the actual number is. 18.432. So we've got 000. That's the millionth place. And we got 18. Okay, so this is the correct number. We just verify it with the data sheet. We went to UART and to the end of the UART area. Okay. 18.432. Okay, so let's go ahead and use that and build program. Okay, the controller is programmed, and you can see that it is turning on and off at 1 second intervals again with the new 18.432 megahertz. Next video we'll be looking at actually doing the communication with the computer using the UART functionality, and we're going to be transmitting and receiving using the FTDI 232 chip or cable. I have a little circuit board here. It plugs into the computer and through the USB, and what it does, this is a USB to serial interface, and we'll plug this into the TX and RX lines of the computer. I'm not going to get into using the COM port on a computer because those are essentially obsolete. I don't know of any computer that has them. They may be on the motherboard, but that is a little bit too much to deal with. So I'm going to go the USB route using an FTDI 232. In a standard COM port, we would do the same thing with a max 232. That is it's essentially a level shifter from 12 volts to 5 volts, and the max 232 swings from negative 12 to positive 12. And I won't be getting into that. If I have any special requests, I may entertain that. But for this project, I'll be using the FTDI. Okay, thank you for watching. If you are following along with these experiments or producing successful projects on your own, helped by these tutorials, please let me know using the Contact Us page on the newbiehack.com website. I would like to feature these on the website to benefit and motivate others to join this creative field. Thank you.